Okay, so today we're starting quadratic functions, which are functions that contain x squared. We have a vocabulary sheet that you picked up, and then we have these notes that we're going to pick up. So we're going to kind of briefly talk about these as we go through this. At the top, you have a review of linear functions. This is all stuff that you should know. Remember, this is what we spent the entire first semester going over. Okay, a linear function, parent function is y equals x, f of x equals x. It looks like a straight line. We have three forms, which are on your formula chart. When I look at a table, I can tell I've got the linear parent function because all the x values and y values are the same. The domain of a linear function is all real numbers. The range is also all real numbers. Now, if I have a situation, obviously that's going to change things. Because remember, a situation puts limitations on our domain and range. All right, so now that's what we did last semester. Now let's talk briefly about let's talk about what we're doing this semester. This semester we're learning about, this unit, we're learning about quadratic functions. So the graph looks like a U-shaped graph. So it looks like that or that. Okay, so you see like this one here, down here, how it's like a U-shaped graph that's pointing up. It could also be pointing down. It will never be pointing side to side. That's a different function that you're not going to learn about in Algebra 1. That's actually not a function, but yeah. So you learn about that in later math classes. So the parent function this time, since a quadratic function contains x squared, our parent function is going to be y equals x squared. F of x equals x squared. Now, we're not going to be looking at x squared right here, but what that's going to look like is, we'll talk about what that looks like tomorrow. I'll draw a poster in class, okay? These two forms are also on your formula chart. We're going to use this one first, and then later on we'll start using this one. I did not used to like vertex form. I thought it was straight up crazy, but now I'm kind of starting to like it. I'm starting to feel good about it. Vertex form, I can find the vertex by looking at this form. Standard form tells, just like with the standard form of a linear equation, standard form is not a graphing form. So we're not going to see anything, it's not going to give us anything helpful really for graphing. The only thing it gives us is the y-intercept is c, and that's it. There's nothing else useful in this form. Okay, so let's talk about what we're going to see when we look at a graph and when we look at a table. I'm going to zoom out just a little bit so we can kind of see them a little bit more together. Let me zoom in just a little bit more, actually. There we go. Okay, so these two graphs, this graph and this table, are of the same function. Okay, so first thing that we see on here, so we talked about quadratic parent function, we talked about parabola. So the next thing, and that is called a parabola. That U-shaped graph is called a parabola. So the next thing we're going to talk about is the vertex, okay? So the vertex is the minimum or maximum point of a parabola. We also call it the turning point. And the reason we call it the turning point is because it's the point at which the parabola stops going in the direction it's going and starts going the other one. So like here, like we're getting smaller and smaller and smaller and smaller and smaller. Whoop, change my mind, we're getting bigger and bigger and bigger. So this point right here is my vertex, because that's the point at which my graph stops getting smaller and starts getting bigger. Or if it was pointing down, the point at which it stops getting bigger, my y values stop getting bigger and start getting smaller. Okay, now likewise, we can find that here. Now your instinct is going to be to go to the middle of the chart, but that's not where we look for, what we look for when we're looking for the vertex. We look at the y values when we're looking for the vertex, and we look for the point where they start to go in the other direction. So see, I have 15, we're getting smaller with 8, smaller with 3, smaller with 0, smaller with -1. Wait a minute, we're not getting smaller, now we're getting bigger. So this right here must be my vertex. Okay, this must be my vertex because it's the point at which my values stop getting smaller and they start getting bigger. Okay, it's where they change directions. Okay, so that's my vertex. That's the first thing we're going to see. Now, if you notice, if you look around here, we have these, if we can actually match up these points around it. We have a point at, we have a point here where they have the same, where they have 0 for the y values. We have a point here where they have 3 for the y values. Okay, so we call these values symmetrical points. Okay, symmetrical points. I like to call them symmetrical pairs because they come in pairs. The vertex is, the vertex is the only one without a pair. So you might be thinking, but these two don't have a pair either. They do have a pair. We just have to extend the graph in order to be able to find them. This one is the one that doesn't have a symmetrical point, and it's surrounded by symmetrical points. You see what I'm saying? So it doesn't have a buddy. Everybody else has a date except this guy. The vertex doesn't have a date. And its pair doesn't have a pair, and it's surrounded by people with pairs. So it's like the sad person at the dance who like doesn't have a date. Everybody else has a date. Like, everybody's dancing around them, and they're just like kind of dancing by themselves. Okay. Now, if we look here, we can see those same symmetrical pairs right here next to us. Let me get like a color. I don't know if we'll be able to see it, but let me try. So if you see right here, we also have a symmetrical pair there. We have a symmetrical pair here. Now, if you notice also the y values, so I have a symmetrical pair at 0, which is some y values I've got. I've got one at 3. You see I've got those y values. Now, I've also got a symmetrical pair at 8. Okay? And so you may be thinking, but I don't see that on this graph. Well, what I can do is, symmetrical pairs have the same y value, so I can put an 8 here. The pattern of my x's continue, so I put a value there for 8. Look, see, there's another symmetrical point. So I can continue the table. If I wanted to, I could keep going again. This has a 15 for y, so it's got to have a 15 here. My pattern continues, and I have 5. So I would have another symmetrical pair at negative 3, 15, and 5, 15. So again, all I'm doing is I'm continuing, I'm matching up the symmetrical values. So the symmetrical pairs have the same y value, and the x continues the pattern that I have in the table. And we can talk about that some more tomorrow if we need to. Okay? So those are my symmetrical points. And let's go ahead and label those too. So there's symmetrical points here, and I see them here. Symmetrical points. Okay? Now, if we have symmetrical points, then that suggests that we have symmetry. So what you may remember is like when you talked about symmetry, like for example, this mouse. For the most part, just pretend these buttons aren't here, it has symmetry. It's a little dirty too, and pretend that's not there either. If you drew a line right down the middle of this mouse, you would have the same thing on both sides. Human beings, well, we are actually not symmetrical, but like a heart is symmetrical, right? See, so if I drew a heart, I could draw an axis right down the middle, and if I folded that heart in half, it would be the same on both sides. Well, that's the same thing we have here. The axis of symmetry is a value that divides the parabola into two matching symmetrical halves, and it runs through the vertex of the parabola. So if I drew a vertical line right through the vertex, that would be my axis of symmetry right here. Okay, my axis of symmetry is, so let's talk real quick. So we have vertex. The vertex has two important points. It's H, K. That's what's awesome about about this form, is it gives me H and it gives me K, which are both important parts of the vertex. So let's pretend that I have a vertex here. Let's pretend that the vertex, so what is the vertex of this graph? Well, the vertex of this graph is 1, negative 1. That means H, K, so 1 is H, K is negative 1. I could put it into that formula and figure out what the vertex form is, which we will do later. Okay? All right, so far we've talked about the vertex, and remember we also call that the turning point. I call it the turning point. It makes it easier for me to think about it. Okay? Now, the other thing we just talked about was the axis of symmetry. Okay, the equation of the axis of symmetry is x equals h. And the h comes out of this part right here. So what is the h value in my vertex? It's 1. So the axis of symmetry here is x equals 1. That is the equation of the axis of symmetry. We're going to talk about domain and range in a couple of days, so we're going to leave that blank for now. I'm sorry this video is so long, but it's just a lot of information. Make sure that you, last thing, sorry, I forgot to tell you this is the last thing, and it's kind of important. I want to point something out. Notice I have two x-intercepts, so I have two zeros. I have one at 0, 0, and I have another at 2, 0. That's because if you look right here, my parabola, since it goes up in two directions, it can cross in two places. So I might have more. I will have I might have more than 1 0. In fact, generally we have 2 zeros, but I mean it's possible you could have 1 or 0, but we'll talk about that later. So you might be looking for more than one y-intercept or 0. All right. Make sure that you write these notes down, study them. Any questions that you have, you need to let me know. All right.